So today I'm going to be talking about conforming Morse Smale complexes. This is a work we did in collaboration with David, who just presented, Josh Levine at Clemson University, Julian Tierney, and Valerio Piscucci. Just a quick reminder, in case you weren't paying attention in the previous talk, the Morse Smale complex is a segmentation of the domain into regions of uniform gradient flow behavior. And basically, we end up with cells clustering integral lines based on their origin and destination. And an integral line is just a path in the gradient that is tangent to the gradient everywhere. If we cluster them based on where they end up, tracing upwards in the positive gradient, we get descending manifolds. If we cluster them based on where you end up, if you're tracing downwards, you get ascending manifolds. And the intersection of these, if your function's nice, is a Morse Smale function, Morse Smale complex. Okay, so they're good for a bunch of things. Actually, if you were in the session yesterday, then David actually presented a new technique on using them to classify bonds in molecules. However, they've also been used for counting bubbles in a mixture, mixing fluids, extracting the core structure of a porous material, computing dissipation elements in a combustion simulation, and many, many more. So in this talk, I'm going to give a brief overview of discrete Morse theory to try to explain what we're doing. And then I'm going to talk about what is a conforming Morse Smale complex. And it turns out it's a very simple algorithm to compute it, but has some very exciting applications, such as you can now compute a Morse Smale complex by numerically integrating streamlines. And you can also take an existing Morse Smale complex and directly edit it without touching the underlying function. Okay, so in discrete Morse theory, instead of a continuous domain, basically this deals with the fact that as computer scientists, we typically get samples at the vertices. Morse theory is introduced by Robin Foreman and has been the basis for most efficient and successful algorithms for computing Morse Smale complexes. So in the discrete setting, we have values at the centers, at the vertices of meshes. Rather than gradient arrows, nice smooth gradient field, we have discrete gradient arrows, which are just a pair of cells. And as David said, this gradient arrow also encodes the flow in the discrete setting. The critical points in the smooth setting are where the gradient vanishes. In the discrete setting, it's just the cells that are not paired. And the index of criticality is given by the dimension of the cell. In the smooth setting, you have integral lines. In the discrete setting, you have V-paths, and these are just chains of cells where you go from the tail of one, or the head of one arrow to the tail of the next incident arrow, and so on. And again, you can cluster things like ascending manifolds and descending manifolds based on either the origin and destination of V-paths. Okay, and the V-paths that connect the cells of your discrete gradient vector field gives you the one skeleton of your discrete Morse Smale complex. Okay, so what do we mean by when we say we compute a conforming Morse Smale complex? So you think that you're sitting there thinking, if I have a scalar function, I have a unique Morse Smale complex for it. It's determined deterministically. But what if you also want to supply a map and in some way have the Morse Smale complex agree with the map while at the same time agreeing with the Morse Smale complex or the underlying scalar function? So in this case, I have two labels in my map, and I would like them to be separated in the Morse Smale complex as well. And this is what we want to achieve by computing a conforming Morse Smale complex. And trust me, it is actually useful. So to formalize the problem, we're given a mesh representation of our domain with some function sampled at the vertices of it. And now we're also given by the user a map that basically labels each cell as with a certain index. So first I'm going to define a conforming discrete gradient field. So I have all my discrete gradient arrows. I say the field is conforming if it's a discrete vector field, and each arrow, the head and the tail of the arrow, the two cells have the same label in my map. And then since if I have a discrete gradient vector field, I have one Morse Smale complex for it, then I say the Morse Smale complex is conforming if the discrete gradient vector field is also conforming. So very simple. So let's look at this. Here's a little mesh that I colored with red and blue. These are two labels. Just to clarify, this is a non-conforming discrete gradient vector field because I have an arrow that crosses labels. And on the right here is one that is conforming. And ended up making these cells critical to make it conform. Okay, so how do we compute this? Well, first, how do you compute a discrete gradient vector field at all? And this is a very broad summary of Robin's algorithm. Basically, you take a vertex, you apply this to every vertex in parallel, or however you want to. You identify its lower star, that is the cells for which it is the lowest vertex, or sorry, it's the highest vertex. You pick a direction and you pair. You create a gradient arrow, and then you perform simple homotopy type expansions to fill in the rest of the space around that pair you just created. And if you do this everywhere, you get a discrete gradient vector field. It's very simple. And actually, if you look at pretty much most discrete gradient algorithms out there, they share these two kernels. In the orange, you identify a lower star and you pick a pair in there. The red part is then you fill in the space between with simple homotopy type expansions. Even if you go to one extreme, like the serial algorithm on the right there, for computing accurate Morse Smale complexes, it's basic geometrically accurate Morse Smale complexes. It's basically the same algorithm, just with the loops in different orders. So we can modify every single one of these to compute a conforming gradient vector field very simply. First, we say, okay, instead of just pairing with any edge in the lower star, you pair with an edge that has the same label. Okay, that's easy. And the second modification is I'm only going to do these homotopy type expansions between cells with the same label. So basically with 2 extra lines of code, pretty much, you're able to compute now a conforming Morse Smale complex. And there we go, wonderful result. So is this just a party trick, or is this good for anything, actually? Well, it turns out it is. So traditionally, the Morse Smale complex was always defined in terms of the flow. And if you're a domain scientist, you may think, well, I'm just going to start integrating streamlines to figure out where the flow ends up. But it turns out if you do that, you can't guarantee the structure of the complex. You end up with things like transversal intersections, crossing streamlines, and all sorts of nasty stuff. On the other hand, with the discrete Morse theory, you're guaranteed robustness. It can be applied in parallel. It's very simple. You still get geometric artifacts. There is an accurate geometry version, but it's serial and slow, and there's no error guarantees. So our idea is to combine the two. So what I'm going to do is, as a first step, I'm going to trace streamlines numerically from every vertex, and that gives me one map. And then I'm going to do the same thing, trace streamlines from every, in this 2-dimensional case, every quad upwards. And where they end up, I'm going to cluster those quads, and it produces another map. Now, my observation is that to get a geometrically accurate Morse Smale complex, I want the arcs of the complex not to cross these label boundaries. So what I'm going to do is I'm going to create a label map that encodes what is a boundary and what is not. So I'm going to define my label map as follows. I'm going to label every cell as 0 if it's not a boundary of either ascending or descending manifolds. 1 if it's a boundary only of ascending, 2 if it's a boundary of only descending, and 3 if it's a boundary of both. So what does this look like? I take my top left vertex. Notice that it's a vertex, so it's not on the boundary of any ascending manifolds. There's only one colored quad adjacent to it, so it's interior. It's not a boundary cell. However, the edge right next to it has 2 vertices, so it's on the boundary of an ascending manifold, but it's not on the boundary of a descending manifold, so I'm going to color it 1, and so on. Finally, I get to a vertex down here. It's not on the boundary of an ascending manifold, but it does have 2 quads differently colored, so I give it 2, and so forth. Very simple process. Now we have our boundary map. So just to reiterate, we take our input function, we trace streamlines upwards and downwards with a dense seeding from downwards from vertices, upwards from 2 cells. that gives us ascending IDs and descending IDs, and we combine these two with the previous technique to generate a label map. And now I just apply my conformal gradient algorithm given the function plus this label map, and it produces a Morse Smale complex that I can do all your standard things with, like simplify. And if I overlay the streamlines, you see that it's still jagged because in discrete Morse theory, we're still stuck on the cells of a mesh, but at least it's a very good, it's about as good as you can get given your streamline. So it produces a nice result. Okay, and it works in 2D as well as 3 dimensions. And now basically we can compute a Morse Smale complex that has as accurate ascending and descending manifolds and the intersections between them as your numeric integration is. So in our case, we just use a simple second order RK method with adaptive step size and error control. And we stopped integrating when our gradient was below some very low threshold. So are we done? Well, in your head you can think, well, I had all these problems with the numeric integration. Where are they in the combinatorial algorithm? Are we trying to fit a square peg into a round hole? And we kind of are. For instance, in this two-dimensional HCCI combustion analysis, I can compute an ascending map and a descending map, and what you'll notice is the boundaries of these two are basically coincident. This is the case where you actually have a transversal intersection between streamlines, which is not allowed in the Morse Smale complex. But based on our construction, the boundary map represents these as adjacent boundaries, and you end up with a valid Morse Smale complex that has simply inserted a bunch of extra critical points where this degenerate condition exists. So you get a valid Morse Smale complex, but extra critical points. There are other such conditions. For instance, doing numeric integration, I can actually go down between cells, so I can get things like this detached region for this label. Now, with discrete Morse theory, I'm stuck to the cells, so when I do my conforming gradient, I actually end up creating a whole bunch of extra critical points there out of necessity. Then there's also other problems, and this is, you could argue this is just our fault for doing integration poorly, but you could get integration instability. For instance, if I integrate in a region and the critical point happens to be on a boundary, so in this patch, everything's moving up and right and ends up either on the right side of that little bundle or on the left side of the bundle, I can label things based on which cell I binned them into by accident. And this is not that outlandish. You could argue that you should just use some kind of distance metric to cluster the labels, but it turns out that there are actually a lot of cases where you have flat-bottomed ridges, and this kind of problem will happen no matter how you end up clustering things. And of course, this will create boundaries in your boundary map and extra critical points in your Morse Smale complex. Fortunately, pretty much all of these are very low persistence and will disappear immediately when you start doing cancellations. Okay, there's one more ugly part here, and that is our numerically integrated geometry is not as nice as you might hope, because the steepest descent on the left here produces grid-aligned geometry, as you would expect. If you look at the sort of the more organic, accurate geometry algorithm that's serial and slow, it produces very nice-looking geometry. And our numerically integrated one actually reproduces very nicely the organic two manifolds, and as well as the intersection of the ascending and descending two manifolds. So these saddle-saddle connectors. However, what it doesn't do very well are the saddle extremum connectors, and this is actually because there's no constraint in our boundary map that forces that saddle extremum connection to actually be positioned with good geometry. It can go wherever it wants, and it chooses steepest descent. Okay, so if there are all these problems, when would you use numerically integrated Morse Smale complexes? Well, those serial algorithms limited to smaller data. The largest I ever got to run on it was a 560 cube, and that took like 14 gigabytes of memory and 12 hours to compute. So if your data is larger than that, then you can try integrating streamlines and then using a simpler conforming algorithm. You have a large shared memory machine with lots of cores, and you want to integrate. So in this case, it would be much faster. Or you have a domain scientist who really, really trusts their integrator. And this is something we've never been able to tell a scientist that, we're going to provide you a segmentation that has this certain error bound. If they come to you with an integrator and they say, we believe in my integrator, and I'm going to believe where the flow ends up, now you can use whatever flow map they give you as input to your topology computation. And of course, there are many optimizations possible, such as right now we do dense seeding of streamlines. You can start thinking about maybe sparse seeding. You can try to start thinking about super resolution boundaries or techniques to accelerate the streamline computation, like streamline compression and so on. Okay, so the second application of our conforming gradient approach is to enable editing of a Morse Smale complex. So this is also not just a party trick. Sometimes your data doesn't actually have the necessary information to construct a feature that you would want to extract. For instance, in the bottom left here, we have a bunch of blobs, and they happen to be connected right here. So there's actually no topological information separating those two. If we compute the Morse Smale complex, those two will be thrown into one basin. Similarly, on the right here, I have a nice signal that is interrupted, and this happens often if you're doing microscopy by either shadows or refraction or something, and therefore the reconstructed topology will also do something crazy. So can we edit these? Well, the key observation is that once I have a Morse Smale complex, that itself generates an ascending and descending label map. So I'm just going to reuse all of my machinery from the numeric computation to create a boundary map and a conforming Morse Smale complex. So in particular, what I'm going to do is I'm going to take my initial data, compute a Morse Smale complex, dump the ascending and descending manifold maps, let the user edit that. In this case, the user has split this region, and then compute the conforming Morse Smale complex. And you could think if you put all of this into a nice swanky interface, then you could actually do this interactively, since the computations are really fast. And you can repeat. You can keep doing this process over and over again. And that was the example where I wanted to split a cell. In this case, I just want to edit the geometry of this line. So I do the same exact process. I dump the ascending and descending map. The user draws in with some nice brush the label they want there, and I output the geometry that the user wanted. And here's a more real-world example where some image processing is done to extract the nuclei of a histology section. You compute the full resolution Morse Smale complex. Now this is far over segmented, so we're going to do some kind of filtering and simplification pipeline to reduce number of features. Unfortunately, I've oversimplified, and there's this green region here where I've clustered now a bunch of nuclei together. Now I can either try to play with all my simplification and filtering parameters, but chances are if I start doing that, they're not local operations. They're in some other part of the data. They're going to create errors in the segmentation as well. So instead, I can just go ahead, output the map, split those regions, and then recompute the conforming Morse Smale complex, apply the same simplification and filtering pipeline, but now that green region is correctly separated. Of course, I glossed over a step, which is in my new simplification, I have to add a new rule that only allows simplification if both critical cells have the same label in my map. Otherwise, I would just any new information I would introduce has low persistence and would be immediately removed. Okay, so we can do that as well. So in conclusion, we presented basically a very simple technique, construct Morse Smale complexes that conform to a user-specified label map. And for the first time, we can use numerically computed streamlines to generate a robust Morse Smale complex. And we've enabled user editing of Morse Smale complexes. In the future, we're going to look at better integration techniques to make this faster, and also explore really developing a user interface to enable the editing to be useful. Thanks.